Okay, so section H, we learned in section H.1 about polar coordinates and polar graphs, and we can use Desmos to graph polar graphs. And you familiarize yourself with polar coordinates in section H.1. In section H.2, we're going to deal with finding areas in polar coordinates. And just like with, you find area underneath the curve, underneath the function. If y equals f of x, you use a definite integral to find the area from limits a to b underneath the function f of x, between the function f of x and the x-axis. We want to find these polar curves also enclose, some of them enclose area, and we want to find those areas. So let me give you a moment to copy this example down, okay, and then we'll go over the solution. Okay, all right, so we want to find the area of the right half of the region enclosed by the polar curve r equals 4 plus 3 times the sine of theta. Now, what's the first thing that we need to do this problem? What's the first thing we need to have? A graph. That's right, Michael. And where are we going to go to graph the polar curve? You can use your TI calculators. Of course, if your calculator, so okay, Colomb and Kahindi like Desmos, and if you use your TI 8384 calculator, if you hit the mode button, there under the fourth line, there's a thing for POL. It says POL. That if you click on that, that puts your calculator in polar mode, and you can type this polar equation then in the y equals menu. Okay, and if you need to see how to do that, YouTube has wonderful videos on that. Okay, but let me just go ahead here then to the solution. So what I did was I used Desmos to graph this polar curve. Okay, and there's a formula in section H.2 that tells how to get the area. Okay, hold on. Let me just, it's in section H.2. It's to find the area of a polar region. The formula is the integral from a to b of 1/2. This is formula 3 in appendix H.2. So the area is the integral from angles, a starting angle A and an ending angle B for the polar region, where the integrand is 1/2 times the quantity f of theta squared. And of course, you're integrating with respect to theta. F of theta, of course, is equal to r. R equals f of theta. So you can abbreviate the formula by writing it as the integral from A to B, angles A to B, of 1/2 r squared. Try to make that a little bit nicer. One half r squared d theta, where of course r is a function of theta. This formula is proven in the book, and I will talk about that formula, how it's proven, on Thursday. But for now, let's just work through an example. Let's apply the formula. So here in the first step here, we'll just block that off there. In the first step, I just applied the area formula. R equals 4 plus 3 times sine of theta. And how am I getting these angles? My starting angle is negative pi over 2, or negative 90 degrees, and my ending angle is pi over 2, or 90 degrees. Well, the way you can get those angles, it's not hard. It's not hard. If you look at where the region starts, the region starts, this shaded region here, the beginning of the shaded region starts right here at this point. And that point, to locate that point, you have to look down 90 degrees. That point has a certain radius to it. Okay, in terms of polar coordinates, I mean, we are using polar coordinates here. That point has a certain radius to it and a certain angle theta. Well, I'm focusing on the angle theta. If I look down 90 degrees, that's negative 90 degrees, I get to that point. Okay? And then the polar curve gets traced out here, and it keeps going, but we're going to stop here because at this point is where my shading stops. Well, that point there corresponds to a polar coordinate where the radius is going to be 7, actually. But theta is 90 degrees. You're looking up. You're looking in a direction of 90 degrees to get to this point. And incidentally, 4 plus 3 times the sine of 90 degrees, it's 4 plus 3 times 1, and that's 7. So are there any questions on the beginning and ending angles? Now, incidentally, someone might say, well, Dr. Duty, instead of 9 pi over 2, could you use an angle of 3 pi over 2? Could you use that? Because 3 pi over 2 is 270 degrees. That's the same, you end up at the same place as you do with negative 90 degrees. But the answer is no, you can't use that, because 3 pi over 2 is greater than pi over 2. So your angles have to go from smaller to greater. So we're not going to use 3 pi over 2. We're going to use negative pi over 2, because negative pi over 2 is an angle, as a number, is smaller than pi over 2. If you think about numbers, whenever you did it, when you do definite integrals, traditionally your bottom limit is smaller than your top limit, and we will preserve that with polar coordinates. Okay, are there any questions on that? All right, well, what we have to do is we have to expand 4 plus 3 times the sine of theta squared. That's 4 plus 3 times the sine of theta. Okay, times 4 plus 3 times the sine of theta. And so what you do is you FOIL that. You FOIL that. And when you FOIL that, you're going to get this result here. You're going to get 16 plus, and notice I pull the 1/2 out in front. You're going to get 16 plus 24 sine theta plus 9 sine squared theta. Now I have the integral of the sum of 3 functions. That can be written as the sum of these 3 integrals. Okay. I have a bracket here. We don't need that bracket. Okay. So I like it that I'm getting through one of these problems today. Hold on. I like it that I'm getting through one of these problems today, because then, on Thursday, you'll be a little bit familiar with this. We're doing an easy one. All right, well now, are there any questions up to this step? Up to this step here? All right, well now what I want to do, I want to see if I can make my life a little bit easier. So for the second integral here, I could get the antiderivative of the sine and and evaluate it at pi over 2 and negative pi over 2. But I noticed that the sine of theta from negative pi over 2 to pi over 2, sine is an odd function, and you're going to have area that is positive or negative here, negative area here, and positive area here that cancels itself out. So this integral here is simply equal to 0. I don't need to worry about evaluating that integral. And the second integral, or I should say the third integral, sine squared theta, is the integrand there. What I've done is I've graphed the sine squared of theta right here about theta equals 0. I've graphed that function from negative pi over 2 to pi over 2. And that function is symmetric about the y-axis. Okay, this area here is equal to this area here. And so that means, see, when I evaluate this integral, I can say that integral will equal 2 times the integral from 0 to pi over 2, because the sine squared theta is symmetric about the y-axis. Okay, so this whole area here, this blue area, would be the same as twice this red area from 0 to pi over 2. And noting that fact makes my life a little, it'll make my life a little bit easier, because you know, it's easier to evaluate trig functions at 0 than at pi over 2. So on that note, may I go to the next page? Are there any questions? We're going to continue evaluating here, but I want to make sure I'm pacing myself okay. All right, are we ready to go to the next page? Well, no, you let me know. You let me know. All right, Michael's good. Thank you, Michael. All right, Candy's good. Snake good. All right. All right. So let's proceed on. Okay, so what I've done now is the area is going to be, well, okay, so the integral of 16 with respect to theta is 16 theta. The middle integral was 0, so we have 24 times 0. And then the last integral, the integral from negative pi over 2 to pi over 2 of the sine squared theta, I'm going to write that as 2 times the integral from 0 to pi over 2 of sine squared theta. I'm taking advantage of the fact that sine squared theta is symmetric about the y-axis. But now what I have to do is the sine squared theta, I can't integrate that directly, but I do know that there's an identity for the sine squared theta. Sine squared theta is 1/2 times 1 minus the cosine of 2 theta. Who's seen that identity before? Maybe, well, in their trig class, trigonometry class. Okay, Michael's seen it, and there's one for cosine squared also. Okay, and so your textbook has a section on trigonometry. If you need to review your trigonometry, in the appendix there's a section on trigonometry. It's let me see here. It's Appendix C, and in there they give identities like this one here. Okay, and it's like a review of trigonometry. So now what I do is I simply start evaluating. Okay, so I'm going to have 16 times pi minus negative pi over 2. That's going to be 16 times pi. And then, incidentally, the 2 here and the 1/2 simplified a 1 and 1. And so I'm going to be left with 9 times the integral of 1 minus cosine 2 theta. Well, 1 minus cosine 2 theta is theta minus the sine of 2 theta over 2. I'm sorry, the integral of 1 minus cosine 2 theta is theta minus the sine of 2 theta minus 2. And so now I'm going to evaluate that antiderivative at pi over 2 and 0. And then I lay out the work very carefully with parentheses. And for the final exam, I would want you to show me this work as well. 2 theta, incidentally, when I put pi over 2 in there, 2 times pi over 2 is pi. and then 2 times 0 is 0. And so you can see how using well, like you can see how like the 0, you know, when you put 0 in for theta, it really simplifies your life. And we know the sine of pi over 2, we know that equals 0. The sine of 180 degrees is 0. And the sine of 0 is 0. Okay, and so when you work it all out, in the end, you should get an area of 41 pi over 4. On this 2 steps up, 16 pi, I express it as 32 pi over 2, so I can add the two fractions here. And WebAssign is going to want this answer. It's not going to want a decimal, and I'm not going to want a decimal either on the final exam. I want the best answer possible. And this is the best answer. I mean, this is, you know, God's answer, as they say, if you believe in God. But you know what I mean. It's the best answer. No computer is going to give you that answer, right? All right, so take a moment to copy it down, and then one moment here. All right, and are there any questions at all on this problem? They can be a little bit tricky. You know, you have to keep track of your angles and your evaluations and all that. That's why it's nice when anytime you can you know use symmetry to help you. It really is helpful, and that is the actual area to the right half for the right half of that region enclosed by the polar curve r equals 4 plus 3 sine theta. All right, are there any questions before I stop the recording here? Okay.